All right, so now that we've got some of the terminology out of the way, as far as graphs go, we're going to talk about how to use them to solve problems. And so the first thing we need to talk about is the different kind of journeys or trips that you can take on a graph, going through some vertices, going along some edges, and stuff like that. So we've got some more definitions here, and I'm just going to show them all because I do need to use this um, graph to show you what I mean by all of these things. So a walk is just a general walk, going through some vertices, walking along edges that exist. So it's basic, and you name it based on the vertices that you travel um, during that walk. Now, if you wanted a trail, that's a very specific kind of walk, and it has no repeated edges. So, for example, if I went from, and let me just, if I went from C to B, and then I went from B to A, and then I went from A to C, and then I went from C to D, then even though I went through vertex C twice, I haven't repeated any of the edges. So that's what a trail is. So let me get rid of that. And now a path is a trail. So remember, it has to have no repeated edges, but now it also has to have no repeated vertices. So I can go from A to C, and from there I can go from C to B, and from there I can go from B to D. And that would be considered a path because I'm not repeating any edges and I'm not repeating any vertices. What I can do is I can close that path. There is such thing as a closed path, which means I'm starting and ending at the same vertex. Some problems involve you starting and ending at the same vertex. So that would be a closed path or trail if it starts and ends at the same vertex. All right, and let me get rid of those. A circuit would be a closed trail, and a cycle would be a closed path. So an example of a closed path would be from A to B, from B to D, from D to C, and then I end up back at A again. Okay. Now I didn't use every edge in the graph, but I did create a closed path. No repeated vertices, no repeated edges, and I started where I ended. So that would be considered a cycle. All right. There are two people that did a lot of work with graph theory. The first one is Euler, and it is pronounced Euler, and he focused his attention on the edges of the graph. So we use the word Eulerian to talk about things that have to do with the edge of a graph. Okay, so here's a graph. I didn't label it or anything. This is just going to be simple. An Eulerian trail uses every edge exactly once. And I'm sure you've seen this before in elementary school where you had to trace this without repeating any edges. And so let me just go through what the solution for that would be. I know you've seen it before. Whoa. What you would do is you would start here and go up here, then up here. It's kind of like going over the roof of the house, not repeating any edges. And this would be the equivalent of an Eulerian trail. Okay. And if a graph is traversable, then it's considered to be a connected graph with an Eulerian trail. That's what we have here. Remember, connected means that you can get from any one vertex to another vertex. So any graph that has that and it has an Eulerian trail that uses every edge exactly once, that's called traversable. An Eulerian circuit is a trail that starts and ends at the same vertex. We can't make one with this graph. And a connected graph is Eulerian if it has an Eulerian circuit, so you can call the entire graph an Eulerian graph if it has an Eulerian circuit, meaning a trail where you can start and end at the same vertex. And a connected graph would be considered semi-Eulerian if it contained an Eulerian trail like this one does, but it doesn't contain an Eulerian circuit. So this example here would be semi-Eulerian but not Eulerian. All right, And now let's talk about the other guy. His name is William Hamilton, and he focused on the vertices of a graph. So let's look at what he talked about. Here are all the definitions, and I'm going to use this graph to do it. A Hamiltonian cycle passes through every vertex of the graph. So what I could do is I could start at 7, go to 6, then go to 2, then go to 3, then go to 4, then go to 5, and then go to 1. So that is, actually that's not a cycle, so let me rethink that. That would be a path, a Hamiltonian path. So let me see here. What I could do is start at 7, go to 6, go to 5, go to 1, 2, 3, 4, and then back to 7 again. Okay, so I've visited every vertex exactly once, and I've ended where I started. So that would be a Hamiltonian cycle. The first example I did was a Hamiltonian path because it didn't end where I started. This is a Hamiltonian graph because it does have a Hamiltonian cycle in it. You could say it's semi-Hamiltonian and Hamiltonian, but basically saying that it's Hamiltonian implies that it's going to be semi-Hamiltonian anyways, because a cycle is a specific kind of path. So those are basically some more definitions about actually walking around the graph, figuring out whether you have to go through a certain number of vertices or not, or a certain number of edges or not. So if you have any questions about this, please let me know, and I will see you tomorrow.